This is lecture number 8, Schedule Design for IE 4355 Facilities Planning. The material for this lecture is covered in section 2.4, chapter 2 in the textbook for the class. In this lecture, there are multiple objectives that are linked to the material that we are going to discuss. For example, that first objective, develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. And objective number 4, be able to design layouts incorporating product, process, and personal requirements. The agenda for this lecture, we're gonna introduce the concepts that are more relevant for this topic first, and then we're gonna talk about marketing information and how that impact the number of products and the production for our facility. Then we're gonna talk about process requirement, and lastly, we're gonna discuss the machine assignment problem. The learning objective for this lecture is to learn how to plan for some of the equipment requirements into a facility, specifically for the number of machines. So let's talk about the concepts. Schedule design decisions provide answers to questions involving how much to produce and when to produce. In addition to how much and when to produce, it's important to know how long production will continue. Such a determination is obtained from market forecasts. The market forecasts are relevant and important for such decisions because we will need to plan for production in the future. So the only information we don't know, I mean, there's uncertainty in those future demands. So the only information that we have on hand to try to make a plan is the historical information, which is based on past information, past data, past orders. So market forecasts can help us determine whether or not we're gonna have more, less, or we're gonna keep our constant production for specific products. To plan a facility, information is needed concerning production volumes, trends, and the predictability of future demands for the products to be produced. The more specific the inputs from product, process, and schedule designs, the greater the likelihood of optimizing the facility and meeting the needs for the manufacturing. So let's talk about the marketing information. As a minimum, the market information given in Table 1 is needed. Table 1 shows the minimum marketing information required for facilities planning. And in this table, we have the forecast in terms of volumes of units that we think we are going to observe in the future for the production of different products. So in this case, we have product or services, and we have 4, A, B, C, and D. And as you can see in the table, we have an expected volume for first year, second year, 5th year, and 10th year. Such volumes can help us plan for our facility in terms of knowing which products will be more relevant and last longer. We can decide in terms of the number of machines that we will set up in the facility, and in addition to that, how those machines will be split between departments. Ideally, information of the type shown in Table 2 will be provided. This table 2 shows the market analysis indicating the stochastic nature of future requirements for facilities planning. So instead of showing deterministic values as in table 1, table 2 shows uncertainty in terms of the expected volume of parts. So as you can see now, we have 3 demand states for each one of the products or services. We have a pessimistic, most likely, and optimistic scenario for each one of the products. And for each one of those scenarios, we have a probability. So for example, the probability of the most likely scenario is 50%. The pessimistic scenario is 30%. And the optimistic scenario is 20% for product A for the first year. Those probability can help us understand that there is an uncertainty in terms of the volume that we will expect. And we can use that information to plan for our future demand. There are same information is repeated for the second year. So you see the most likely scenario in this case has a higher probability. Same thing here as we move to the 5th year, and then by the 10th year, that product will be making more of our production. Or actually in terms of the most likely scenario is the one that is assuming the higher probability, which has more certainty in terms of the number of units that we should produce. And in that case, the pessimistic scenario is very low. The probability is very low, 10%. And same information is presented for products and services B, C, and D. If such information is available, a facilities plan can be developed for each demand state, and a facility designed with sufficient flexibility to meet the yearly fluctuation in product mix. So knowing that uncertainty, or at least having good estimates of the uncertainty and the stochastic demand, we can design for sufficient flexibility that will allow us to change or to adapt to those fluctuations. In addition to the volume trend and predictability of future demands for various products, the qualitative information listed in Table T should be obtained. Table 3 lists the valuable information that should be obtained from marketing and used by a facilities planner. Some information or questions: who are the customers of the product? And then in terms of the facilities planning issues impacted by the information include the packaging, the susceptibility to product changes, and also to changes in the marketing strategies. Where are the consumers located? That can help us plan for the location of the facility, the methods of shipping, and the warehousing system design. Why will the consumer purchase the product? Is it something that is based on seasonality, like Christmas decorations? Is there any variability in sales, like for products that are typically purchased for school? So you might see variability in sales. Packaging is also relevant. And where will the customer purchase the product? Is it something that you build by you buy per unit, or do you have to order? Again, packaging is relevant. What percentage of the market does the product attract, and who is the competition? So knowing who is the competition is very important. Can help you plan for future trends and growth potential for the manufacturing. What is the trend in product changes? Space allocations, material handling methods, and needs for flexibility. So let's talk about process requirements. Process requirements, specification of process requirements typically occurs in 3 phases. The first phase determines the quantity of components that must be produced, including allowances for defective items in order to meet the market estimate. And we discussed that in one of our first lectures, how to compute the number of units to be produced by taking into account the defective items. The second phase determines the machine requirements. So that's our focus in this lecture for each operation. The third phase combines the operation requirements to obtain overall machine requirements. The estimation of number of machines required, the total number of machines required begins with the identification of the machine use by individual operations. The machine fraction for an operation is determined by dividing the total time required to perform the operation by the time available to complete the operation. The total time required to perform an operation is the product of the standard time for the operation and the number of times the operation is to be performed. So let's look at one example. If it takes half an hour or 0.5 hours to process one part, and if the 6 parts are to be made in 2 hours, then it follows that 1.5 machines are needed to complete the operation. Whether or not 1.5 machines are actually adequate to complete all 6 parts depend on the following. Are the parts actually being made to the 0.5 hour per part standard time? Is the machine available when needed during the 2-hour period? Are the standard time, the number of parts, and the time the machine takes known with certainty and fixed over time, or does it change? So all that information is important in order to make that final conclusion. So let's look at those questions. Are the parts actually being made to the 0.5 hour per part standard time? This is handled by dividing the standard time by the historical efficiency of performing the operation. Is the machine available when needed during the 2-hour period? This is handled by multiplying the time the equipment is available to complete the operation by the historical reliability factor for the equipment. The reliability factor is the percentage of time the machine is actually producing. Let's look at the third question. Are the standard time, the number of parts, and the time the machine takes known with certainty and fixed over time? If considerable uncertainty and variation exists over time, it may be useful to consider using probability distributions instead of point estimates or the deterministic values for the parameters and utilizing a stochastic machine fraction model. So the idea is to model the uncertainty in terms of the time variation for processing the parts. If you are familiar with simulation modeling, that's what we do. The idea with simulation is to be able to replicate, or at least to model, the uncertainty of processes, and then using those probability models, we can replicate the performance of a process and then determine what is the actual output based on the uncertainty. Typically, such models are not utilized, and the approach taken is to use a deterministic model and plan the facility to provide sufficient flexibility to handle changes in machine fraction variables. So the reason this statement is made, such models are not utilized, is that sometimes the people that are in charge of making these plans are not familiar with tools such as stochastic optimization or simulation modeling. The following deterministic model can be used to estimate the machine fraction required. Here we have the equation for computing the number of machines required per shift, which is depending on the standard time per minute in minutes per unit produced, which is S in this equation. Q is the number of units to be produced per shift. A is the actual performance expressed as a percentage of the standard time. H is the amount of time in minutes available per machine, and R is the reliability of machine expressed as a percent uptime. The numerator stands for the total time required per shift, and the denominator in this formula indicates the total time that one machine is available per shift. So let's look at this example. In this example, we are trying to calculate the number of machines required for this process. A machine part has a standard machining time of 2.8 minutes per part on a mini machine. During an 8-hour shift, 200 units are to be produced. Of the 480 minutes available for production, the milling machine will be operational 80% of the time. During the time the machine is operational, parts are produced at a rate equal to 95% of the standard rate. So the question to be answered is how many milling machines are required? So for this example, we can establish the values for the parameters needed in the formula. So going back to the formula, we have S, the standard time, Q is the number of units to be produced, E is the actual performance, H is the amount of time available per machine, and R is the reliability of the machine. So in this example, S is going to be equal to 2.8 minutes per part. Q is equal to 200 units per shift. H is equal to 480 minutes per shift. E is 95% or 0.95, and R is 80%. So we can substitute those numbers into the formula. It's 2.8 times 200 divided by 0.95 times 480 times 0.80. And this is equal to 1.535 machines per shift. As you can see, this is a fractional or a fractional number. So if you're planning for the number of machines and you get a fractional number, the rule of thumb is to go to the next integer value. So F is going to be 2 in this case, because we can now have 1.535 machines. The last part of this lecture looks at the machine assignment problem. In this section, we consider how decisions regarding the assignment of machines to operators can affect the number of employees. Specifically, we consider a situation involving the assignment of operators to semi-automatic production equipment. It is assumed the machines are identical. To illustrate the situation on the configuration, see Figure 1 in the next slide. It shows the activities of an operator and 3 machines. So here's Figure 1. So here we have the timeline on the first. So timeline is here. Sorry. So here's the time. These are the operator, what the operator is doing through the time. Then we have machine 1, machine 2, and machine 3. So L stands for loading, T for traveling, and then we have idle. UL is for unloading. I and P is inspection, and so on. So so you can see for this operator, it's taking care of these 3 machines, And as we move forward in the timeline, he'll be loading, unloading these machines as needed. Excluding the idle time, each machine cycle requires A plus T minutes to complete the cycle. Likewise, the operator devotes A plus B minutes to each machine during a cycle. Hence, sorry, I should look at this first. So under conditions similar to those depicted in Figure 1, a deterministic model can be developed to determine the optimal number of machines to assign an individual operator. And we're going to be taking into account all these parameters. A is the concurrent activity time, for example, loading and unloading a machine. B is independent operator activity time, looking at walking, inspecting, packaging. T is the independent machine activity time for automatic machine time. N prime is the ideal number of identical machines to assign an operator, which is what we want to know, if 3 machines is enough, or do we need to assign 4 because he has too much idle time? Or the contrary, maybe we have assigned 3 and he doesn't have enough time to take care of 3 machines, so we might need to go to 2. So M prime is the ideal number of identical machines to assign an operator. M is the number of identical machines assigned to the operator. TC is the repeating cycle time. IO is the idle operator time during the repeated cycle. And IM is the idle time for each machine during a repeating cycle. So excluding idle time, each machine requires A plus T minutes to complete a cycle. Likewise, the operator devotes A plus B minutes to each machine during a cycle. Hence, an ideal assignment is given by this equation. N prime equals A plus T divided by A plus B. For the example, A equals 2 minutes, B equals 1 minute, and T equals 6 minutes. Therefore, N prime equals 2.67 machines. Since a fractional number of machines cannot be assigned to an operator, consider what will happen if some integer numbers of machines, M, is assigned. The word content for the operator with total M times A plus B, while machine cycle will be A plus T in duration. The repeating cycle will be larger than of the two, and the difference in the two will be the idle time. If M is greater than M prime, then the repeating cycle will be M times A plus B in duration. If M is less than N prime, then the repeated cycle will be A plus T in duration. Therefore, TC is going to be equal to A plus B if M is less than or equal to M prime, or M times A plus B if M is greater than M prime. IM is going to be equal to 0 if M is less than or equal to M prime, or TC minus A plus T if M is greater than M prime. Finally, I0 is going to be equal to TC minus M times A plus B if M is less than or equal to M prime, or 0 if M is greater than M prime. TC is the repeating cycle, IM is the idle time for each machine, and I0 is the idle operation time, as discussed on the previous slide. So using this information, as we saw in the previous example, we were able to compute the number of machines required for a process. And then if the machine requires an operator, we can use this strategy to determine how many machines to assign to an operator. And that's the last part of this lecture. So in this lecture, we focus on the discussion of schedule design, and we look at marketing information, process requirements, and machine assignment problem.